Thank you, Dinesis, for such a good introduction. So, well, hello, welcome everyone. I know it's a last lecture, and I see there were people watching match last night until past midnight. So, I hope some people are still sleeping. So, okay. So today I'll talk less on AI and more on robotics. So let's more combine HRI part. So it's more like, wait a second. I'll try to talk on robotics, classical robotics, and how it's being updated now with a lot of HRI and other things to go on to the real world implementation. So, the title of my talk is From Robot Navigation to Human Aware Robot Navigation, which I will discuss the foundations and some of the emerging trends. So these will be the contents of today's talk, and before I go into the topic of the discussion, I'll try to introduce myself. I did my master's and bachelor's at IIIT Hyderabad, as Dennis mentioned, and then I moved to LAS, CNRS in Toulouse to do my dissertation in proactive and situation assessment for human aware navigation, and now I'm doing a postdoc with Serena where I worked on human aware motion planning. But previously I was working on a couple of reinforcement learning and humanoids and a lot of simulators and a lot of the things. You can see some of the videos from my previous work here. So now we go to the robot navigation part. So what exactly is a robot navigation? So it's simply put in, we just make the robot move from one place to another place while avoiding the obstacles and possibly reaching a target or a goal. It sounds simple, but there are four major questions that are often raised by the community, like how does the robot know about its environments and surroundings? How does the robot know where it is in the environment, and what is the best route to reach the goal, and how should the robot move? So these are divided into four different branches, I would say. The first one is perception and mapping, seeing and perceiving the world, building a model of the world. And the second one is called localization, which is again a different field of robotics altogether. The third one is called path planning, although it's not quite I would say used only in robotics. It's there everywhere, but it's one of the part that is essential. And finally, the trajectory planning and control, which I think is the most important part, at least for this talk. So each of this is a different research field, as I said, and we'll be focusing on these two parts majorly in this talk. And now I'll give a brief introduction of the different things. So robotic perception is basically, as I said, the ability to understand the world around from its sensors. So we already have a lot of talks from computer vision community in the previous days mentioning about different approaches and everything. And we also have a lot of openly available libraries we can use for doing all of this. You can see like detection, segmentation, point cloud based segmentation and everything. So this is more or less available now off the shelf, which we can deploy on the robots, provided we have enough computation. And now the mapping. The mapping can be different depending on the type of sensors you employ, the amount of memory you have on board, and the type of environment you are navigating. The simplest form is the 2D navigation grid, which for a mobile robot or anything which is navigating in a planar surface. If you are navigating a 3D surface where you need to see the walls and other things, you employ a voxel grid, which is 3D extension of the occupancy grid. And there are also other approaches like point clouds and mesh approaches. And finally, there are things which are not really a representation of the environment directly, but a graph that represents where everything is. It's like how we build, okay, there's a door here, to the left of it there is a cafeteria, there's a room on the right side of it, something of that. This is where a topological maps comes in. And then finally a hybrid map where we combine everything. Since we use ROS navigation a lot, at least I have been using it a lot, so the most common types that are available and easily deployed are occupancy and the voxel grids. And you might ask a question, what about the mapless navigation? So there are mapless navigation is often short horizon. That means it can do a visual navigation to some extent, but in order to move from one place to another place with a knowledge of the environment is required. At least I think a topological map is required to do a long horizon planning and navigation in the map using mapless techniques. And now coming to localization, again the process of determining robot's position in an unknown or known environment. We have different techniques that do that classically. So the first one is dread reckoning, which is basically you keep counting how much you moved using the encoders and the IMU on board without having any feedback from the environment. If there is a slip or something, you have a mismatch in your data. So finally, then there are probabilistic localization, which is, I think, very commonly used and deployed in many of the current robotic systems, which follows different techniques that are, again, I'm not going to explain the techniques, it's a summary of them. So it's a Kalman filters that use most probable next state using a Gaussian model, and then basic Markov localization, which uses some markers in the environment to detect all the possible states and then do a maximum possibility estimate. And then the classical, the most commonly used one, Monte Carlo and adaptive Monte Carlo, which are employed by the community because they are very easy to implement and they are lighter versions of Markov localization. And then of course there's SLAM, which is helps us to localize and build the map at the same time, which is often used in the environments where it is unknown and we need a map before even we can navigate the environment. And then finally the GPS. Yeah, it's very good for outdoors and autonomous vehicles and everything. As soon as we come to indoors and places where the signal cannot reach, we lose that advantage. So now I'll talk about path planning. I don't know, maybe it's like the classical thing that has part of the any robotics course, I feel. So it's simply you try to find a path from your starting position to a goal position in your configuration space. A configuration space usually is a set of all the possible configurations of the robot which are free or colliding with the obstacles. Basically, it's a description of the space that allows us to search for a path. So, for a 2D navigation, the configuration space is a special Euclidean group of two, which has 3 degrees of freedom, x, y, and theta, since we are planar and move forward and sideways and then rotate. So again, there are two kind of techniques to do the path planning. One is the grid-based path planning, where you build a grid of the map, like an occupancy grid, and search for a path from start to goal. And then there is sampling-based path planning, which does not require any kind of specific grid representations. So in a grid-based search, you just search the grid for the path, like the Dijkstra, A-star and everything. And in the sampling-based one, you have a binary information of where there's an obstacle or not, and then you try to explore the environment and find the most feasible path that can take you to the goal. So the grid-based paths are good for low-dimensional workspaces, especially for navigation. 2D map is quite memory efficient. Whereas if you go to 3D maps and 3D occupancy, it's better to use sampling-based ones because they're much faster. Yeah, small discrete spaces, large continuous spaces, and then the advantage with grid-based path planning, they are always shortest possible paths you can find in the environment, whereas the sampling-based one does not always guarantee a shortest path. It's suboptimal, but it still works. And finally, some of the algorithms, which are, I think, every one of you know, the Dijkstra, A-star, theta star, and everything, and then RRT star, PRM. You can read about them. They are pretty famous. So now I will come to the main part, the trajectory planning and control. So when you talk about trajectory, it's often the definition is not very well defined, because the trajectory just means a path with that has information about the positions, the velocities, accelerations, and everything that makes the robot move, along with the kinematic constraint satisfaction. And control is a process of basically making the robot move through this or trace this trajectory. Often they are combined because it's hard to separate them. You define a trajectory, you find a best possible thing, and you try to apply that control command to your robot. So I would combine the definition. I would say it's a process of generating a desired time-based motion for a robot and continuously computing control effort, trying to follow that trajectory, and also also responding to disturbance and avoiding the avoiding obstacles. So you should note that this is, when I talk about the control in this lecture, it is often different from the low-level motor control or joint-level control that is often mentioned using PID or other kind of things. This is more on high-level control where we employ horizon planning or a short kind of reactive planning or reactive control, sorry. So the reactive control, for example, it just tries to avoid the obstacle whenever it's trying to approach in the last minute, like some of the classical approaches, artificial potential fields and reciprocal velocity obstacle are some of the famous ones. And ORCA is like a extension of reciprocal velocity for the optimal possible way. So it's just an optimization problem with reciprocal velocity. And I think if you are using ROS, you know DW and DWB with just a simple dynamic window approach trying to follow a path. And then there are receding horizon or predictive approaches like timed elastic band or model predictive control or model predictive path integral control or MPPI. All these things tries to have a look ahead, like they plan the trajectory well in advance, like you can see the green path here. It's looking well ahead and trying to make an informed decision rather than taking an immediate reactive decision. And finally, there are learning based ones, which I cannot see how they fit into any of this. They do react, but they also see a long horizon thing. So they would say they are a different class of planners altogether. So now I would try to show some difference between reactive and long horizon planning that is useful for human robot navigation. The first thing is, suppose the robot is trying to reach a goal, and if the reactive planning does this, like it tries to optimize its path to the goal and then just do the immediate reaction when the human is in its vicinity. So it's usually myopic, it's just an avoidance, and then it's hard to avoid like deadlocks where you might not come back from. So whereas a kind of long horizon planning allows you to estimate this in advance and stops you from doing such kind of action that will end up in a deadlock. And it's usually a huge trajectory is planned, and then you take the best action possible to reach the next part. So, I mean, this is just a note. So, long horizon planning is better for human-aware navigation as it avoids the occurrence of anything before it even happens. So, what's happened? Okay, one second. Seems like everything is solved, right? I mean, navigation is always said a well-solved problem. It's been like not really yes?
Sorry, I have a question. What is that block?
What?
What is that block in the previous? Yes.
Which one?
Yes, yes. Deadlock. What's it for?
Deadlock. Okay. Deadlock is like situations where, for example, you are crossing a door and you have no space to move back or react in such situations. And then if you have a reactive planner, if you see any social force model or something, it always in the narrow passages or doors, it always gets stuck. It cannot move. It just happens that there is no feasible control at that point. So you can avoid it if you, because there is not enough space to move around. So the kind of, I would say, cluttered situation where you have not enough space to move around. Yeah, so since navigation has been solved for I would say decades, and these are all old methods. Yeah, now let's see the real world implementation. So all this works very good for our robots that work in warehouses, and the robot vacuums are quite nice these days. They are much more efficient, still slow but still efficient. Now what about the autonomous vehicles? Even though these techniques were old, autonomous vehicles are still a big part of research. And still this has a very structured environment, fixed set of traffic rules to follow, and localization is not an issue at all. And I was seeing some statistics online. Apparently there's a website that documents every crash with an AV from 2014. So I saw the statistics and I saw that most of the faults and accidents that are happened are not because of technology, it's humans. If you see the major over 800 accidents were because the other driver was stupid or whatever they were doing. It was the fault of the other driver or the driver inside the autonomous vehicle. So it is the human intervention that caused more accidents than the technology itself. Of course, there is like 100 or around 100 accidents because of technology, but it's nowhere near to what humans factors are adding up. So yeah, I would say even in structured environments, in the wild deployment has so many issues that needs to be solved because of the humans. And now imagine everything is unstructured, there are no rules, and then everything is uncontrolled. That's where we are entering human-aware social robot navigation. We try to employ them in offices, airports, wherever there are rules but not strictly implemented, or at home where there are no rules from time to time. So yeah, so starting with the definitions, okay, maybe not before definition. Ask the ChatGPT to generate an image, giving the title of my talk, and it's what it generated. So it's a good image. Kind of shows what exactly it is, but also misses a lot of things. So some of them, again, it's a structured versus unstructured environment, rules versus no rules or adaptive rules, and predictability versus almost unpredictable or uncontrollable, and then zero to no human interaction, low human interaction to very high interaction and constant assessment. So now with the definitions, I mean, since there is no formal definition, we try to come up with a definition in one of our works, which is the principles and guidelines paper. So you might have seen this definition already if you are at the paper. It's like social robot, navigating robot acts and interacts with the humans or robots, achieving its navigation goals while modifying its behavior. So the experience of agents around it is not degraded or even enhanced. So and also we also define some properties for it, like it should detect and treat the humans as a special kind of obstacles with the utmost priority, and its behavior is designed to minimize the disturbance and cause little to no confusion to the humans, and the navigation intentions should be shown explicitly or implicitly. It should be understandable to the person who's co-navigating or present in the environment. And finally, in the case of conflict, the robot should make an action that is potentially harmless and even at the expense of compromising its own task. Again, these are some of the definitions we have come up with. Not the field is still evolving, so there are more definitions that will come up soon. And what does it require? The major part. So human representations and their predictions, interaction and communication capabilities for the robots, contextual and situational awareness, decision-making capabilities, and finally, modified planning and control strategies that can work in all the situations. So, okay, now you talk about the human-robot interaction part. So there's a lot of HRI part from now on. So before we go into that, I'll try to introduce why I see human-aware navigation as a part of human-robot interaction. Classically, it has been always used in the scenarios where there's a task planning, try to complete a task along with humans. So navigation was instead of using a navigation which is not responding to humans, it's better to have a navigation that is responding to humans, understanding their human actions, communicating, acknowledging, and also collaborating in complex situations. I see it as joint action actually. So if you see the definition of joint action, it can be regarded as a form of social interaction where two or more agents coordinate their actions and bring about a change in the environment. I would try to highlight the parts which I think are important. It's a social interaction, which navigation is, coordinate their actions in space. They have to if they are co-navigating or doing some kind of navigation in corridor or in a crowd or someplace, and change in the environment, which I would say is positions of the agents or the whole crowd dynamics of the environment. And I have come up with some of the properties I would call the joint action principle for human-aware navigation, which are based on the joint action principles for HRI, but they are in the context of human-aware navigation, which is sharing the common perspective like social norms, collision avoidance, context, etc., coordination, trying to respond, free the way, wait, etc., and predict others' contribution, trying to understand what the other person is trying to do and how do I respond, and finally communication to negotiate and do the kind of understand what the humans are doing and also tell the humans what it is trying to do. And then we come to the components and approaches. So you might have heard the proxemic theory if you anywhere close to social robot navigation. It's the most famous theory that has been regarded as so far the gold mark for implementations, evaluation and everything. So this was done in 1966, pretty old, and for humans, not for robots. Robots were non-existent at that time. And then what happened was Edward Hall presented different spaces, distances from the human where there's intimate space, personal space, social distance and public distance are defined for different kind of activities. So the social navigation community in the initial days, they took this idea and then made concentric circles that represented these zones and tried the robot to make the robot to avoid this intrusion into these zones. And over the time, there were multiple shapes and different things that came up. For example, there was the elongated shape where people don't care much about their bag, but the front should be more elongated. And there was oval, like sides are okay, but back and front should be equal. And then objects of interest, it's not just the human to human, there are all objects and the human. So you also should not avoid a human seeing a painting, for example. You do not go between the painting and the human. And then there's also information processing space where when the human is moving, you have the information, you have a decision making space just in front of the human where the zone of interest for, let's say, moving. And then finally we also have adaptive approaches that adapt to different kinds of obstacles or poses. For example, sitting, standing has a different kind of representations and everything. So now from individual modeling, we also have group modeling. Like Kendon came up with this definitions called F formations, O space, P space and R space, which were trying to present different two-person configurations in different kind of letters. You can see N, V, C, H and L. These are the common kind of letters that are used for this representation. And then again, for group representation, the social navigation community again took this in, made a representation for the groups based on these, and then they defined costs around this. So, and then for more than two people, it was always a circle, so there was also O formation for them. And now what about issues? So first issue is that these are meant for human interaction, not human robot interaction. So you often see the robot is safe, but never guarantees the comfort from the humans. It always reported that they don't feel comfortable even according to the proxemics we use and depending on the robot we use. There are so many other factors that were not really well studied. So in some of the recent studies, I'm talking about a couple of years, like probably 24, 23, we have a series of studies that were conducted by Neger and the team. They were trying to see how all the proxemics and the velocities play out. So some of these findings were like passing at the back of the person was more uncomfortable than actually passing in the front. So the zone should be elongated in the back, not in the front, especially if it's a non-humanoid robot. And a humanoid robot at the back was more uncomfortable. I don't know why this was the result, but it was people were more uncomfortable when a humanoid robot passes behind them. And of course, the speed of the robot was affecting their comfort. The more distance, then the higher speed you can move in. But as you come close to the human, the lower speeds were preferred. And finally, overtaking and pass by are not the same. Like I'm talking an example here, but usually every situation has to be dealt differently, and it's not really the same. So I would define a human as a special kind of dynamic obstacle with expectations, states, and capabilities that are not often well defined. So this is where what we are dealing with to start this whole human aware navigation part. So now modeling is good, but what happens if the human starts moving? We have predictions like simple motion prediction, just updating the trajectory based on the velocity and the history. The simplest form of this is the constant velocity prediction. You take the previous velocity you have calculated over the time, and you extrapolate that okay, the human will be moving with the same velocity for the next couple of seconds where I am trying to do my planning. And then there are advanced technique like a lot of neural network based techniques that does human or crowd predictions. You can see a lot of papers on this online. So some of the main idea is that you take the history into account, try to predict multiple possibilities. It's more a stochastic approach where you take the highest probable path, or you have the whole variance plus mean kind of approach and tries to avoid the whole region. And apart from motion predictions, one note. So some of the recent studies were shown that constant velocity prediction is as good as any of these. So for robot navigation, I'm not saying the complex predictions are bad, but constant velocity prediction is enough. Mainly it is because there are so many things that are not really deployable in the real world. For example, these are highly computationally intensive. You cannot deploy them on any simple robot, and often for a short horizon, constant velocity is same as the horizon. The complex mechanisms we are using. So that's some of the reasons why it's not preferred. And then there are intention predictions where the robot, where the human is going, what is the human doing, and trying to take an informed decision rather than just avoiding obstacles. So for the autonomous vehicle, there are a lot of research on whether the pedestrian is trying to cross or not. If the pedestrian is trying to cross, they try to make the stop of the vehicle. Basically, there's a lot of research on just one part, like is the person crossing or not. And now there are VLMs that are helping them do the same thing. They give an image and ask if the person is trying to cross or not. And then human aware navigation is much more complex. We also have to talk about interaction. If the human is trying to come to me for interaction, or if there is an intention to cooperate, or if there is a place the human is intended to go. Some of the works that worked on this in this field were like using a face-based orientation. They were like, okay, if the human is looking directly at you, the robot, the human is trying to interact. And then using motion prediction and some kind of labels around the exits, you also have this intention prediction of where the robot might be headed to the exit or to other place in the environment. And now next part is the communication. So communication allows us to avoid one of the important things in, again, crowd navigation or any contextual navigation, where you may have a freezing robot problem. Anyone knows what a freezing robot problem is? Okay. So typically in any kind of crowd situation where the robot cannot find any control or a path to move forward, it just stops. It just stops and it just waits for it to clear the way. But in a very crowded situation, it stops forever. It just freezes and then cannot find any feasible path at all. So in such situations, we humans we usually we say excuse me, give me way, or we just push through or do something. Robots are not allowed to do that; they just freeze on the spot. So this is called the freezing robot problem. So this is where the communication part is quite useful to avoid this kind of situations. So there are different modalities which have been employed by the community. So for like the explicit communication things like a speech, visual, and audio based communications. I mean, some of the things from the that are used, again, not in the real world, but more like experimental. There you on the top you see a projector being showing the path where the wheelchair is trying to go. In the middle one, you can see the robot is showing what it's trying to do in literally stopping, moving, and turning. And in the last one, it's more like human inspired. They put a head visualization. When the robot is turning straight, it's going straight. It's moving. When it's turning left, it's going to the left, and etc. And then there was this approach that was explored, exactly the freezing robot problem I was discussing, where the robot kind of either collides or times out before reaching the goal because it cannot find any path, it just stops. So they introduced this kind of, okay, if I cannot find a solution for a certain amount of time, I start beeping. So the robot beeps and the humans kind of go away or provide the way for the robot to pass through, kind of showing, okay, its intention to move forward. And now this is a little more, one more step. They use speech, first saying, okay, excuse me, I need to pass in kind of situations. If even that doesn't work, they just hold their hand and kind of showing, okay, I need to pass. Kind of a gesture plus speech saying, I'm passing through, thank you. So different things. And also there are some other things like showing acknowledgement is also very important. You see on the top you have gestures where a robot is trying to turn and move sideways in an aisle, which was found to be more warmer compared to the robot which was moving straight, even though the robot footprint is the same, it's round. So people felt this gesture was more warm and welcoming than a robot that just passes by. It's like humans. If you are trying to allow a human to go in a narrow corridor, you just turn to the side. And finally, there are traffic lights. Basically, it's like a car that is indicating lights on different directions, along with some gestures, okay, kind of rotating to one side, left or right, when it's trying to move to the other side, move to the direction. And finally, there's also implicit communication, which is not directly visualized or explained, but kind of expected behavior from the human. So, for example, if I'm going to in a corridor or any place, if I'm just moving left and right, it's always confusing for the other person who's there. So it always choose one side and stick to it. So this kind of choosing the side is also kind of a communication, or slowing down and stopping. Like instead of stopping suddenly, you slow down and stop. Kind of you have a previous intention. Okay, the car or the human is slowing down, so they are trying to stop. And then there are combined methodologies that combine both of these two. And it has been shown in a lot of studies that this kind of improved the legibility of the robot and also shown to have positive responses, as I was telling you in the gesture-based study. There's so many other studies you can find where it was proven that this is necessary, but not many systems do effectively employ it. Finally, there's one more, so many other component is awareness. I would say awareness is the ability to perceive and understand and be conscious about something. In the context of robotics, it's to perceive, interpret, and understand its environment, its state, and make an informed decisions to perform tasks. So there are different kinds of contextual information we need to take into account. For example, environmental context, a hospital and airport is not the same. I should be aware of that and should behave appropriately. Whereas in a spatial context, like a door and a corridor and a room are different contexts, and an elevator is altogether a different context. Room and elevator are not the same. We have to be aware of that. A situation, kind of situation is a child, I'm dealing with a person with disability, or I'm in a hospital delivering some drug. I need to know And I also need to know the self, like what speed I am moving, what is the acceleration I can stop at, and what is my size so that I can go through the whole environment. And of course, humans and cultural, which are age, their mobility, their intentions, and social norms, etc. And if you have seen this paper, you might have seen all these scenarios. We have collected a lot of possible scenarios that can occur in a human-robot co-navigation situations. On the top, like a frontal approach, or overtaking, following, intersection, showing gestures, entering, leaving elevator and rooms, joining, exiting groups, and so many traffic scenarios. So you can find all these scenarios in the paper, and these are some of the scenarios that have been widely used or for testing in different papers. But there are also some scenarios that they are missing, like for example, you exploit the space. I would say you can move at a full speed when you still have enough space around the robot, around the human, but you don't need to always, and when there is no low space, the proxemics are compromised, the speed is compromised, everything has to be different. So this kind of awareness is also necessary. And in the blind corners, you also need to be aware that there might be humans, so it's not just about avoiding a blind corner, but also being aware that there might be a human. And finally, there is a passage through the door where, again, there is a possibility of humans around, so you have to be careful there. And then human awareness, like when you are overtaking, you also have to make sure that you do not overtake at a large speed or at a small angle, surprising or causing shock for the humans from behind. So this is for the robot, of course. When the human is trying to overtake the robot, we don't have any rules for it, but yeah. And also you should be aware of the mobility, if the human can actually react for your actions or not. So because if the human is carrying a huge load, he cannot or she cannot really move to the side or give way for the robot to move. And then there are situation awareness, like, okay, there are queues and the flow of the traffic, which are similar to the ones previously I showed. There was no queue scenario previously, so I mentioned the queue here particularly. And then we move into the cultural part. So cultural part is a big discussion. So not really many works have this cultural part included into their frameworks because it's quite hard, and now the efforts are being taken by the whole community to establish a lot of intercultural data sets. There are multiple data, I would say, works and collaborations these days in the social robot navigation community, where they were talking about how do we collect the data from different culture to learn different norms and probably train a VLA or VLM to kind of distinguish this. And we now move into the situation assessment and decision making part. So as I was saying, the situation assessment, you should understand where you are and you should make a decision. So for example, I may get stuck in a passage. So this is one of the deadlock scenarios where you have to make a decision and do something which is not straightforward, and or coming in or going out of the elevator, which is again depending on the density, depending on the situation, time, you might have to take different decisions. And then you face a human with reduced ability at an entrance or a child or something, and then either the robot has to wait, go ahead because the human has given a sign to go away. All this, the assessing and understanding the situation is important to make a decision. And then finally, decision is the part where you choose the right action to inform this decision. And now there has been, I would say this is my definition, not really a classical one. So I would say it is necessary to make situation assessment decision making to have a smooth, legible and human acceptable robot navigation. It could be something like knowing when to stop, wait, or go in a situation, follow in a situation. It's for crowd navigation, which works quite well because this is what the humans will do usually. Or when to yield or wait for the human and give way for the other agent when they need to move forward. So this kind of understanding, making a decision and executing all this whole process is required to make better navigation. So also went to assert urgency in an emergency or something, or how do I react in an unseen situation? I should have a way to react, especially usually it's a stop, but stop is not always the optimal one in many scenarios. So especially in autonomous cars, if you stop in the middle of the road at 100 kilometers per hour, it's going to be an accident. So you don't always stop. Now the main part, planning and control. So I'll try to move this quickly. So we have at the global planning level, we have a lot of approaches that focus on the human modeling part, as I showed previously. They just add different kind of cost maps, different kind of approaches, cost-based approaches, and the algorithms remain the same all through the years. I haven't seen many changes for the last 2 decades. So the major kind of approaches are like they are individual cost maps for the humans, or a group kind of cost maps where they kind of combine Kendon's theory, and then the time dependent cost maps which kind of predicting the cost into the future and then doing it just a global planning, no controller or something, you just follow the path. And then there's topological maps that kind of tries to include the social norms like moving left or moving right, depending on the environment you are in. And then finding the things like a queues or crowd in a situation through, I mean, say, convolutional neural network based learning approaches. And following on the global planning, there have been CNNs that were used for planning paths and cost maps. So one of the work by Perez, they were using CNNs to plan the global path using a top view of the I would say situation. They provide a snapshot of the situation and tries to ask the network to give, output a global path. And this was simply trained using RRT data, and it was good, but I'm not sure how this is quite useful in a situation. It's global plans are usually quite vast. But one of the recent papers, they were generating more like a generalized cost maps based on synthetic data. They generated a lot of synthetic data in different situations, trying to focus on things like groups, hallways, queues, etc. And the network is dynamically updating the situation, reading the situation, and updating the cost map to do a socially appropriate cost map is what I would say. And now we move to the local planning, which is the controller part. Now, one of the most important controller if in any human aware or social robot navigation is the social force model, which was again designed for the humans to see how the humans move in an environment. It's a very theoretical one where, okay, I have an attractive force towards the goal I'm going, I have a repulsive force towards the obstacles so that I don't collide into them, and a controlled attraction between the pedestrians in a group. And then it's simply add all the forces, take a force vector, and once you have that force vector, you calculate the velocity for the human to move or the robot to move. So this was applied directly to robotics. Again, a lot of works on that apply to different situations, like for example, the crowd navigation and the accompanying task where the robot is accompanying a human, and finally the also approaching how the robot should approach using the social force. They play with the forces and modeling to kind of achieve this. This is kind of nice because it's a simple modeling, but it works. Now I talked about the timed elastic band approach, which is more long horizon planning. The previous one was more short and immediate planning. This was a more long horizon planning, where the timed elastic band is basically you build a hypergraph with vertices and the time difference, with the poses and the time difference as vertices, and all the constraints you want to have, the acceleration, velocity, obstacle avoidance as the constraints, and then you solve it using a graph solver. This is G2O is a graph-based solver used widely in SLAM, but is also applied to this kind of navigation problem. And then this was extended in my work to human-aware navigation. It's called human-aware timed elastic band, and we do a co-planning where we extended the whole graph with the different constraints. You see the red one here is the constraint for the robot, The yellow ones are the constraints between the humans, and the social constraints are the ones in the vertical in blue. So we make this big graph and tries to solve it, and then it gives us some very interesting results. For example, it allows us to have a adjustable effort sharing depending on the situation, and elicits a solution in the places where cooperation is required, and then it adapts to the context based on, of course, we have introduced the behavior trees to adapt to the context, and then we also have special algorithms that does the blind corners. And now, of course, the more famous model predictive control. It has been adapted, of course, by many works. Some of the works I try to point out here are like this one is using DB scan based clustering. So they do, instead of individual or simple navigation, they try to cluster the groups, and they define a special optimization problem to solve group MPC. They call GMPC, and then the group is also evolving with time. Instead of dealing with the single human prediction, they do a group prediction, and then this is used in their MPC to solve the optimization problem. This is quite interesting to see moving from individual to group. And then there is a recent work which is quite famous, called the SIGNAV, that employs MPC and the kind of cooperative planning, assuming that the human is always using an ORCA model, which is basically a simple obstacle avoidance model. They try to solve this huge complex optimization problem that using KKT constraint. It's a very mathematically intense paper, but the idea is you are assuming that the human is moving like an orca, basically avoiding using reciprocal velocity. And now there are other approaches in learning, of course. There are plethora of RL based crowd navigation approaches. Everything is similar in recent days because they were doing a kind of PPO or DDPG or whatever the reinforcement learning that is famous, and then adding the cost functions to that. Some of the notable works I would say is like one of them. It's a SHCADRL, which is quite famous. They use a multi-agent network to learn the social norms in the environment. They try to see if I can use passing on left, going on right. They try to see if they can do multi-agent prediction and also navigation at the same time. And there is another work that does a D-step prediction, making a relational graph. It tries to see how the human and the robot are connected through a relational graph using a graph neural network, and then use this to have a D-step look ahead prediction like a long horizon and make a velocity decision at the end of the planning or learning, I would say. And finally, one of the recent ones that was published in DRO, they use PPO to train the DRL policy. The main thing the difference I saw was the reward was modeled using velocity obstacle. The direction in which the robot should take a turn was basically calculated using a velocity obstacle formulation. So apart from that, I think more or less reward modeling and a lot of end-to-end frameworks. There are many works that are existing in the field. And finally, there are some of the new recent ones, the flow matching. So this is one of my work on the right, where we was working on having Priest, which is a trajectory optimizer, and then we generate multiple trajectories using it, and we use the flow matching to choose the best one out of these trajectories. And I saw the similar work that does the same thing, but instead of using the Priest, they're using MPPI, which is, I think, similar. They do they have the sample candidates and they choose the best sample candidate based on the situation. And then finally, I think I'll be done in like 5 minutes, but yeah. So now the VLMs part. So what is VLMs and LLMs doing to social navigation? So the first thing, they have solved the reasoning situation. We can reason about what and where and what should I do in a situation, given that I have the input and fast processing on my robot. So for example, the robot here is trying to make an information, okay, the humans are forming a group and talking, so I should go to the left instead of going through them. And then there's also works like that does group detection using VLMs. It just input an image and ask the VLM to classify the groups and differentiate the groups, and then they does the navigation on top of that. And then this is one of the interesting works I found where they were distilling the different situations for the VLM and then using the situation based assessment to make a decision, which is, I think, quite interesting, since this is one of the most relevant problems in the field, is what I feel. And then there is a behavior adaptation. So in this work they were doing different kind of cost maps based on the input, like I don't want to use the stairs, I want to use the stairs. So the cost map is adapted based on the prompt, and you can update the navigation just using the cost map. And finally, the user adaptation. So depending on the user, you can adapt to their preferences, you can adapt to their choices without having the load of doing high computational or high processing, as we previously, if you have some good API calls to your VLM, it can do work in real time, I guess. And then I would say this is what I saw 2 days ago. It was released by Mistral, so I will just play that video. That is for. Okay. Yeah. You see, there's, I think, a couple of more minutes. So the main idea was, when I saw this, I was like, okay, maybe did they solve the social navigation problem? But no, they just solved the navigation problem again. So I'm like, okay, why? I don't know. Visual navigation is good, I understand, but you spent a lot of resources on building this. I'm not criticizing their work, but I'm saying it could be easily expanded to social navigation, since VLMs have the ability to do it. So I'm hoping in the future we'll have a good social navigation model from this. Again, there are so many things that need to be studied. So if you are in the field, don't be discouraged, because there are human-robot interaction part, there are communication part, there are so many other things that are still not really well understood. So there's so many other things you can do. And of course, the controllers are evolving day by day, and everyone does not have a budget to have a VLM running forever, of course, and the hardware constraints are there. So making simpler navigation algorithms is always a good choice. So now I come to the challenges part. So what are the main challenge? Anyone know in the field? Yes?
Not in the field, but I have some questions.
Yes, sorry.
Maybe as a challenge.
Yeah.
For VLM, you are training it on a visual material. So
Yes.
if I change the furniture or someone appear in the scene,
Sorry?
for VLMs for social navigation.
Yeah.
I haven't, I'm not familiar how you are taking the videos, but I would imagine if the furniture got changed or someone pull a chair or appear on the
Okay, this part I would say it's majorly handled by the navigation algorithms itself. The collision avoidance is not just static, it's dynamic. There's a laser or a camera that is constantly updating the state of the map or the environment to the robot. So the planning, everything is updated on the time. I mean, this is actually not quite new. It's been done for decades now. The dynamic obstacle, it's called the dynamic obstacle avoidance. So you always keep updating your environment, you keep updating your map at, I think, the 10 to 20 hertz, and then you deal with this in a replanning manner rather than trying to learn over the time. Like there are also things like, okay, furniture has changed place. Over the time you can learn, but usually in simple navigation framework, there's like, I don't care, I have an empty map, everything else is a dynamic obstacle, I try to avoid whatever I see with the laser. Yeah. Okay, so I think the challenges part is the evaluation. So no one knows how to evaluate a social or human-aware robot navigation honestly. There are no metrics which are measurable. There are limited data sets, and there are no benchmarking standards for the community. So also there's a HRI part that makes it complex because we have to do user studies, large scale ones that can have statistical significance. So it always time and more money. Sorry. So these are the common metrics that are used in the field. There are a lot of navigation metrics like path length, timing, success rate, and everything. Social metrics that are mostly based on proxemics, distance to the human, and everything. And then these are pretty simple, but they don't quite do the justice. So some of the works, one of my work, I was working on establishing a different kind of metrics that can act as proxies for danger or surprise, where I was studying the danger in the events of overtaking and crossing and pass by, danger in terms of fear and pass by, which measures how far if the robot is approaching head on or if the robot is moving at a fast pace, and how the human might feel based on these situations. And a surprise where there is a blind corner where the robot is trying to overtake you or trying to come from a blind corner, how can the robot measure these kind of situations which are quite complex to understand. And so I use some of the fields from neuroscience. There were like recognition and react time, and try to devise some metrics based on these things from the neuroscience. And then I saw a recent one from, I think it's Wenzel, I think they are from Bosch or Honda, I'm not sure. So they were working on defining this two metrics called intensity and responsibility, especially in a crossing scenario, who takes how much responsibility, how intense the behavior is. So these are some of the new metrics that are being designed in the field, but not very, I would say, widely used or adapted at this point. We are still doing user studies. We are still confirmation that these work well, and then probably one day we might see them. And finally, this is almost my concluding slide, like the concerns about the real world deployment. There are so many urban regulations that needs to be taken into account before we can even employ the robots anywhere. And there is no good infrastructure for the robots, so it's not meant for any mobile robots at this point. So we need a different kind of robots. Maybe humanoids or quadrupeds could be the answer. And many concerns about the privacy. If you have seen Shelfie, the robot moving around, we have been asked a lot of questions. So if it is the case with the people who already know we are not collecting a lot of data, then imagine people in outdoors talking about the robot deployment, they're scared. So like, is the robot recording me? Will you use my data? You will sell my data to China? It's like so many weird questions we have. And then of course, user acceptability. Not everyone likes a robot. That's a fact. And we have to deal with them. If your robot is moving in an environment with a lot of old people and maybe not a lot of them don't like it, you have to make sure, design the algorithms or make the things adapt so that it's, I would say, approved or used by the people who don't like it. I mean, it's a kind of challenge. So, and finally, I would ask the question: can we actually say robot navigation is completely solved? Depending. Theoretically in a lab, yes. Practically, no. Okay, now these are my long list of references I used for this talk. And finally, we'll have a hands-on human-aware robot navigation tutorial in the afternoon, where we try to design our own controller, mapping, and in other things. So see you all in the afternoon, and I'm ready to take any other questions.